All right, hello and welcome to day 10 of Advent of Code in C++. Today we have a problem called pipe maze. So this one is a little bit more involved. So basically, we're given a two-dimensional grid of tiles, and every tile has a certain type. So it might be a vertical pipe, a horizontal pipe, or one of four 90-degree bends. And it's like a little bit annoying because these 90-degree pipes are like kind of hard to look at. It's like hard to see sometimes, especially when the grids get like really complicated. But it's okay, we'll work through it. So basically, it gives you some rules for each type of tile, and then a dot is ground, and S is the starting position. And the idea is that there's one large continuous loop within the grid. And so, for example, here's an example, or so here, yeah, here's like a loop. Um, this is what a loop might look like. And it's not always a square though, like it could be a little bit more complex. So here is a slightly more complex loop. And the idea is that in order to get out ahead of the animal, you want to find the tile in the loop that is farthest from the starting position. And then you want to return how many steps along the loop it takes to get from the starting position to the point farthest from the starting position. So to simplify that a little bit, because this is kind of a strange problem statement, the first thing we should observe is that the answer to this question is just the length of the loop divided by 2, or floor divided by 2, I should say. Right? Because if you have a loop of length 16, right, in order to get to the point farthest away from the starting position, you clearly just need to take 8 steps. And it might be easier to see here where you have a loop of length 8, you just need to take 4 steps. Or I guess in this case, it's a loop of length 7. So anyways, we can solve this by basically finding where, so first we need to figure out where we're starting, right? Because the start isn't always in this 1, 1 position. I think here it's in a different position. Let me just open this. So yeah, here it's in a different position and so on. And so we're going to start by finding where that S is. And then what we're going to do is we're basically going to go through and so starting with the S, we're going to test different directions. So we're going to see, okay, can we move up or down or left or right? Thankfully, only we need to check 4 directions. We don't need to check all 8 or all 4 cardinal directions. We don't have to check like northeast and those 45-degree angles. And so we're just going to write a series of basically if statements. And we're going to use a queue. So this will be a queue-based approach. And essentially, if we find a valid position, we will try to move in that direction. And if we can, we will make that move. And then finally, by the time our queue is empty, we will have discovered the entire loop. And then we'll simply return the length of the loop, again, floor divided by 2. So let's get right into the implementation. I'll start by creating a new day, day.sh, and then I'll call it on day 10. And then I'll cd into that directory so that we are in there when we want to compile our code. And then I'm going to grab the test input. So there's actually 2 test cases. We'll start with the easier one. Let me grab this. Sometimes triple clicking works and sometimes it doesn't. So, or I think it always does. I think just sometimes I don't hit the triple click because I'm using a magic mouse, which has its limits. And then we need to here include the queue so that we can access it from the standard library. And then I'll scroll down to where it says begin solution here. And our input is basically already in the format we want it because at least for me, I read my input as a vector of strings where each string represents a line. And that's exactly how we want it stored in this graph or grid or however you want to define this. I call it a graph. And so I'm just going to set the graph directly equal to the input. And then I'll declare 2 variables, start row and start column. And I'll I'll begin by iterating through the graph and locating where my starting position is. And this is pretty straightforward. And so I'm going to initialize a Boolean value called inner did break, which will basically just prevent me from doing extra iterations through the rows once I identify the starting position. It's not strictly necessary. It's just I don't know. I don't even know if it's like best practice. It's kind of like the equivalent of like a for else loop in Python, if you're familiar with that. And so here I will say if graph RC is equal to S. Then we want to set SR equal to R and SC equal to C, and then we can set inner did break equal to true, and then we can break out of this inner loop. And then here, if inner did break, we will break out of the outer loop as well. Great. By the way, I want to mention before we get started, this entire solution is credited to Hyperneutrino, at Hyperneutrino on YouTube. He did a wonderful series on Advent of Code. He's done it, I think, for a couple years. He is one of the most eloquent explainers of these solutions, and I highly recommend you check out his videos, probably before you check out mine, because I'm sure he'll explain the actual theory behind the solution much better than I can. So I don't want to go any further without mentioning his great work. And so yeah, hopping right back into the code. So once we've identified our starting row and starting position, we can then initialize our queue as well as a set called scene. And in this set, we're going to store pairs, so basically just coordinates on the grid that we have seen. And this set is going to basically define our loop. Expected a declaration. Okay, so something is wrong here. I think probably I need to include a set maybe, but I'm not entirely sure. There we go. That should resolve the issue, I hope. Yep, okay. And then we're going to start. So because we're gonna start at the S, we're gonna append or insert the starting row and starting column into our scene set. Great. And then we're also going to initialize a queue, also of pairs. So it'll be S standard queue and then pair, and that we'll store integers in the pair. We shouldn't need long values for this. I believe the grid is small enough. And then I'll just call that queue, and then we're going to queue.push the starting pair. Make pair of SR and SC. Great. Okay, so now we have our scene set, which contains just this tuple or pair, and then we also have our queue, which now just contains the starting row and starting column. Great, and now we can say while queue is not empty, we want to do some, this is where kind of the actual solution happens. So we're going to say our current pair, or current position, I should say rather, is equal to queue.front, and then we need to pop that value off of queue so that our queue actually decreases in size over time, or like we don't look at the same values twice. And then we'll say int r is equal to cur position.first, and int c is equal to cur position dot second, and then we'll say current character is equal to the graph at r at c. Okay, and now we want to check all four directions. So we're going to check up, and then I'll just copy this. We'll check down, left, and right. Great. And so when we check up, what we want to do is we want to basically see if we can move up. So if r, first we need to check that we're going to be inbound. So if r is greater than 0, and now we're going to check a kind of compound OR condition. So if we, in order to see if we can move up, our current character has to have an up connector, right? So there's 4 characters that have up connectors. It's S, or I'll write it as a string, S, the vertical bar, J, L, and or just these 4, right? So any of these 4 characters are characters from which you can move up. So what we're going to do is we're going to say, actually, let me put this here so that it's a little bit clearer. So basically, this is like the source, and then we'll also have like a target, right? We'll have a series of characters that can accept upward movement. And the characters that can accept upward movement, those are going to be also the vertical bar, 7, and then F. Okay, so we're going to say we need to be able to move up from our current character. So the current character has to be equal to either S or the vertical bar, or J, and then finally it could be equal to L as well. Great. And we have to be able to move to the next character. right? So let's say that, and the next character, if we're moving up, would be at r minus 1 c. So we wouldn't be changing columns, we would just be changing rows. And then so we're going to check whether it's equal to the vertical bar or it's equal to 7, or it could be equal to f. Graph r minus 1 c equal to f. Okay, and then let me wrap this around. Okay, so now this is our entire condition. And then we need to check one more thing, which is that we need to make sure that the position that we're looking at moving into, so the position at graph r minus 1, well, the tuple would be r minus 1 comma c. We need to make sure that this tuple does not exist within the scene set, right? So we want to say and scene.find of this tuple. So, but it's actually a pair, so we need to make it a pair. Make pair of these values. It needs to be equal to scene.end because that means it was not bound. Great, and that looks good. And so if I'm just gonna keep it kind of unwrapped just so we can not have to look at it. But I'll wrap it again when we write that down. And so if this is the case, right, if we can move up, then we want to insert the current, or we want to insert the next value. So std make pair of r minus 1c. We want to insert that into scene, and then we want to push it onto q, right? So just like this. And then I'm just going to copy, and we can make very small modifications for down. So for down, the target, or sorry, the source, we need to be able to move down from our source, right? So those characters would be S, the vertical bar, F, or 7, I believe, right? And then if we're moving down, we need to be able to accept down at our target. So those would be the vertical bar, J, or L, capital J or L, right? So basically what we can do is now that we're moving down, so now that we'd be adding 1 to R, we need to make sure that we are in bounds. So we need to do R is less than graph.size minus 1. And the reason it's minus 1 here is because, again, we'd be, rather than subtracting 1, when we move up, when we move down, we're actually adding 1 to R. So let me actually just select all these and change them to R plus 1. Okay, and then rather than checking, so here we keep the vertical bar, here we change the J to an F, and here we change the L to a 7, and then we change the 7 to a J, and the F to an L, and we should be good. Wonderful. Okay, so now to check left, it's again very similar, but rather than checking the row, we now want to check the column. So we do C is greater than 0, and then we want to make sure, rather than modifying the value of R, so we'll just keep R as R, we're going to modify the value of C. So it'll be C minus 1 because we're moving left. And if we're moving left, we need to be able to accept left, or we need to be able to move left from our source, right? So it could be S, it could be the dash, it could be J, and it could be 7. And then the target, those are going to be, let's see, it'll be L because it needs to be able to accept leftward movement. So it could be L, F, or the horizontal dash, right? So I'm going to modify this if statement, and I guess I could just keep the 7 the same. And then the J will become an L, the vertical bar should become a dash, and the L should become an, or this L should become an F. Wonderful. Okay, and then, all right, I already did the C minus 1. Okay, and then finally for the right, it's just going to be basically the inverse of this. So again, we'll change this to less than graph r.size minus 1. And then rather than the J, we want the F. Rather than 7, we want the L. And then rather than the L here, we'll do the 7 and the J. And then the last modification that we want to make is just changing the C minus 1 to C plus 1 because we want to move right. Okay, so quite a bit of conditional kind of shenanigans there. But now we can just say that our answer is equal to scene.size divided by 2. So we'll compile this, and then we'll do, okay, just kidding, there was an issue. Okay, so must be a typo somewhere. Okay, yeah, here we go. So I want this to be, let's see, I want this to be a J and a 7. Okay, so crun p1.cpp, and then, I don't want to cd. I want to do /p1 on the test input. And the answer that I get is 3, which I don't think is correct. I think we want it to be 4. Yeah, so let's see what's happening here. Okay, so just a typo, as most mistakes when you are programming happen to be. I think it should fix it. I had r plus c rather than r plus 1. I guess I was just not paying attention. Okay, yeah, so 4 is the correct answer, and then if we run it on the real input, or my real input, we get 7,086, which is correct, I believe. Okay, so part 2. We want to figure out the area enclosed by the loop. Okay, so if we look at the loop above, the area, or the loop only encloses 4 tiles. So let's figure out how that works. So the start goes around here and it loops, or I guess if you follow it down, it loops through and it goes all the way up and then down. And so these dots that appear that they're like on the inside are actually on the outside, because you can see that the loop does not actually contain them. The loop only contains these 2 dots, right? Or these 2 tiles. And here's a good depiction of that. So, and here is a lot more complex loop where the answer, I guess, is 8 tiles. So what we want to do is figure out how many tiles are enclosed by the loop. And Hyperneutrino has a really, really very insightful explanation to this. But the whole idea is that, let's say you are starting at this tile, for example. If you look across, so if you kind of like traverse horizontally across the grid, and you cross the loop once, that means that a tile that you encounter is, if you cross the loop an odd number of times, essentially, that means that that the loop will enclose a tile. But if you cross the loop or cross a pipe an even number of times, that means that the loop does not enclose the tiles, right? So these dots, because they occur after 2 crosses, are not enclosed. But for example, here, this dot, because it occurs after just 1 cross, means that that this tile is in fact enclosed by the loop. So again, please, I refer you to Hyperneutrino's video. He explains it much more thoroughly than I do. But the idea is that we want to count essentially how many times we cross a pipe horizontally. And you could also do it vertically. I think it's just a little bit easier to write horizontally, but there would be no issue doing it vertically. Scanning vertically, I mean, right? Because the same would be true. If you cross the pipe an odd number of times vertically, then the dot or the tile would be enclosed by the loop, and if it was even, then it would not be enclosed. Okay, great. So let's implement that. So if we head back over, I'm just going to grab all of our code from part 1 and paste it into here, and then I'll just make this slight modification. Great. Okay. So now what we need to do is we actually care. So in part 1, we didn't care like what S was. We just tested all 4 directions. But in this case, we actually do care what S is. And so what we're going to do is basically try to figure it out. And luckily, we can just use the if statements we've already written to figure it out. So we're going to initialize, in addition to the set and the cube we already have, we're going to initialize a set of characters called possible S. And we're going to insert all of it'll start by containing every value or every pipe, right? And so I'm just going to paste this a bunch of times, and then this vertical bar will become a dash. We can use J, L, 7, and F, and those should be all of the values we need. Okay, and so now we're basically going to just check every time. So not every time, but like we're gonna deduce what S is. And so what we can say is if we are looking up, and our current character is an S, that means that we have to be able to move up from S, right? So we're gonna basically find the intersection, the set intersection of possible S and the set vertical bar J and L, right? Because we have to be able to move. So we want to set possible S equal to its intersection with this set. And I couldn't find a way to do that cleanly in C++. And so basically what I did is I initialized a copy set I just called it copy set equal to possible S. And then I iterated over copy set, copy set.begin, it not equal to copy set.end. And then I basically erased elements that I used the iterator to erase elements in possible S that didn't also occur in here, because that's the definition of a set intersection. And the reason I didn't just iterate over possible S is because the size of possible S would change, so the reference would be messed up. And so that's why I ended up needing to make a copy. So we have to dereference it, or the iterator, and as long as, or if the iterator is not contained, or if the value that the iterator is pointing to is not contained within this set, and so basically that would mean that it is, or that the iterator is not equal to a vertical bar, and it's not equal to a J, and it's not equal to an L, then we want to erase possible S dot erase that value. Great. And then by the end of this while loop, we should just be left with one value for possible S, or possible S should be of length 1. And so if we're checking down, then of course the values are going to be different. It's going to be the vertical bar, the F, and the 7. So here it'll be F, here it'll be 7. And then I'll copy this. Well, actually, I already have it copied. Here, if we're checking left, we want to check the dash, the J, and the 7. So I'll just change these two. And then finally, if we're checking right, we want to check the dash, the L, and the F. Okay. So yeah, once the while loop is completed, we will know what our possible S is. So we can say character S is equal, and we'll dereference possible S dot begin. Great. And then we want to replace S with its correct character, basically. And keep in mind, we've already stored where the loop starts in the SR and SC value from part 1. So we'll say graph of SR, because we can't reassign values directly in strings, but we can reassign values in vectors. And remember, graph is a vector of strings. So we're going to say graph SR is equal to graph SR dot substring from 0 to SC, or from 0 and then of length SC plus S, which is just a character, plus graph SR dot substring from SC plus 1 to the size of graph SR minus SC. Or again, I keep saying 2, but really the second parameter is actually the length of the substring. And this will effectively replace the character at SC with S. Great. And now what we want to do is fill our graph. So let me just write this line. So we're going to create a new graph, and basically what we're going to do is everything that's outside of scene. So remember, scene actually, or what we're calling scene is really our loop. So I'm actually going to redefine the variable scene. I'm going to select all instances of it, and I'm just going to call it loop, because that's what it is. And every character that is outside of our loop, I'm going to replace with a dot, or a tile, I should say. And that will be our new graph. So for int r is equal to 0, r is less than graph.size, r++. And then for int c is equal to 0, c is less than graph r.size, c++. And then I want to define for every row, I'll define a new row. So vector of characters called new row. And I will say if the current character is, or if the pair RC is in our set, R comma C, is equal to loop.end. So this would actually mean it's not found. We will push, or I guess I called it new row. We will push a dot because that means it's not in our loop. Otherwise, we will push just the value at graph RC. Graph RC. Great, and then we will push every new row onto the new graph. Dot push back new row. Wonderful. Okay, and then what we can do is we can figure out which values are outside, or which tiles are outside of our loop, because it actually turns out that that's easier than figuring out which values are inside. And then we can just do some simple math using a set union to figure out which values are inside, or to count how many values are inside. So what we're going to do is we're going to initialize a set of pairs of integers, just like we have before, and it will be called outside. And then we're going to iterate through, actually I'm just going to copy these two lines. Oh, I did not mean to delete everything. I'm just going to copy these two lines, or this code block, so I don't have to rewrite the iteration. Now we're going to iterate through new graph though. New graph. And rather than defining a new row and creating a new graph, we are going to do some operations here. So we're going to define a Boolean called within, and we're going to set it equal to false. And we're basically going to keep track of whether or not we are currently within the loop based on which characters we've crossed over. And we're also going to say Boolean, we're going to define a Boolean called up, which is equal to false, or by default equal to false. And this will just tell us kind of like which way we're pointing. So what we'll do is we'll define our current character equal to new graph, R and C. And then we're going to say if character is equal to a vertical bar, then we're going to set within equal to the opposite of within, right? Because this means we basically crossed a pipe. Otherwise, if the character is equal to an F, or the character is equal to an L, we will say up is equal to whether the character, so it'll just be that it'll be false if the character is not an L, and it will be true if the character is an L, right? Because this just means that we are pointing up, right? And then similarly, if the character is a J or a 7, not an 8, a 7, then we have a slightly more complex if statement. So if the character is a J or a 7, if up is true, we want to check if the character is not equal to J, we want to set within equal to not within. So we want to reverse within. Otherwise, if not up, then we want to set the character, or if not up, then we want to check if the character is not a 7, and then we'll also set within equal to not within, right? So either way, we're kind of doing the same thing here. We're just switching within to the opposite of what it is now, because that means we've crossed a pipe again. Okay, and then, but either way, regardless, so if we're at a J or a 7, we also want to set up equal to false, because both of these characters point down. Great. And then finally, we'll say if not within, so if we are outside, we will outside dot insert the pair R and C. Wonderful. Okay, and then our answer, rather than being equal to the loop size divided by 2, is going to be equal to the size of the new graph. So it'll be basically the area of the new graph should be 0. Okay, and then we're gonna, so this is just the area of the new graph, right? It's the number of rows times the number of columns. And then we're gonna subtract the outside union with the loop, because that will give us what's inside of the loop. So I'll define a new variable called outside union loop, and we'll get its size, and this will be our answer. And the way we're going to find outside, so outside union loop is going to be a set of pairs, once again, pair int outside union loop, and then we're just going to use the set union function, which will accept, so it accept the beginning of our first set, the end of our first set, the beginning of our second set, the end of our second set, and then we have to pass in this inserter function, inserter, and we call it on outside union loop and outside union loop dot begin. And that should be all we need. And if we go ahead and compile part 2 and run it on the test input, we get 1, but that we want to use this test input, or a different test input, I should say. So let's use this. So I'll go ahead and paste that in. We do get 4, which is in fact correct. And then if we run it on, let's do a, I guess, a more challenging input case, we should get, we're expecting 10. So let's just check that. We do get 10, and then I'll run it on my real input. I believe we get 3. Okay, so that's wrong. We want 317, but we're getting 323. Interesting. Okay, so I'll do a little debugging and check what's wrong, and I'll be right back. Okay, so this one was also a pretty straightforward mistake. In fact, I think I said this, I just didn't write it. But we only want to modify the values of cur s, or possible values of s, if we actually run into s as a character. So we just want to wrap all of these intersections in this if statement. So let me just do that real quick. So if cur ch is equal to s, then we'll do this. I'll fix the indentation as well. And this should give us the correct answer. So if, let's see, try to do this quickly. And I think there's just one more. Perfect. Okay, so if cur ch is equal to s. Yeah, so this just makes sure that we only modify the possible values of s if we actually run into s. Otherwise, it doesn't make sense. So I'm actually surprised the answer was as close as it was. Okay, yeah, there we go. We get 317. And I had some more debugging output down here that I will just get rid of. So if we run this, we get a nice clean 317. Wonderful. And that's exactly what we need. Perfect. All right. Thank you so much for watching. I do hope this was helpful. Again, please do check out Hyperneutrino. He has some great content for the Advent of Code. But yeah, I'll be back tomorrow for day 11.